You've probably heard it before. Split an atom and you get unimaginable power. It sounds almost magical, like cracking open a tiny bead of matter and releasing a trapped sun. And if we're honest, there's something deeply disturbing about that idea. How can something so small, so invisible, contain enough energy to flatten cities? It feels wrong, it feels disproportionate. It feels like we've uncovered a glitch in reality. But here's the bold claim. There is nothing unnatural about splitting an atom. What's disturbing is that it works exactly the way the laws of physics say it must. And Richard Feynman understood this better than almost anyone. Feynman used to say, if you think you understand quantum mechanics, you don't understand quantum mechanics. But the atom, that part at least we can approach. Let me ask you something. Have you ever held a rock guided? It feels solid. Have you? Stable? Almost eternal? Now imagine this. The stability of that rock is an illusion born from a cosmic tension, a delicate balance between forces that would happily tear it apart. Every atom in that rock is holding itself together under extreme internal pressure. And when you split one, you're not breaking something calm. You're triggering something that was barely stable to begin with. At the center of every atom is a nucleus. Protons and neutrons crammed together in a space unimaginably small. Here's the strange part. Protons are positively charged. And like charges repel. So why doesn't the nucleus explode instantly? Because there's another force, a stronger one. It's called the strong nuclear force. And it is the strongest force in nature. Stronger than electromagnetism. Stronger than gravity. It acts like an impossibly powerful glue, binding protons and neutrons together. But it only works at very short distances. Think of it like this. Analogy number 1, the compressed spring. Imagine compressing a powerful spring between your hands. The more you compress it, the more energy you store. Now imagine that, instead of your hands, it's fundamental forces squeezing matter into a tiny core. The nucleus is like that compressed spring. In heavy atoms like uranium, the nucleus is enormous by atomic standards. There are over 200 particles packed together. That's a lot of positively charged protons trying to push away from each other. The strong force barely keeps them together. Barely. It's like stacking too many magnets together with their like poles. Facing, you can force them close, but the tension grows. Now here's the disturbing part. When you split that heavy nucleus into two smaller ones, the total mass of the two pieces is slightly less than the original. Where did the missing mass go? It became energy. E equals mach squared. Not metaphorically, literally. Einstein's equation isn't poetry. It's bookkeeping. Mass and energy are the same thing, wearing different clothes. When you split uranium, the resulting fragments are more stable. Their internal tension is lower. And that difference in stability, that tiny difference in mass is released as energy. A lot of energy. From something so small. But why so much? Because the speed of light squared is an enormous number. Multiply even a tiny mass by that and you get something staggering. Now let's zoom out. When a uranium nucleus splits, it doesn't just release energy. It releases neutrons. Those neutrons can hit other nuclei, which split, which release more neutrons, which split more nuclei. This is a chain reaction. It's like lining up millions of mousetraps, each loaded with ping-pong balls. Anagony number 2. The mousetrap room. Imagine a room filled wall to wall with mousetraps. Each one has 2 ping-pong balls balanced on top. Now throw a single ball into the room. One trap snaps. It flings 2 balls into the air. They land on other traps, which snap. Within seconds, the entire room erupts into chaos. That's a nuclear chain reaction. Energy was already stored in the traps. The first ball just triggered the release. The disturbing realization. The energy in nuclear fission is not created. It was always there. So, why doesn't everything explode all the time? Because probability says no. This is where physics becomes subtle. At the microscopic level, everything obeys quantum rules. Probabilities, wave functions, uncertainties. A uranium nucleus sits in a delicate balance between staying intact and flying apart. Most of the time, it stays intact, but occasionally, spontaneously, one will decay. It tunnels through its own energy barrier. Quantum mechanics allows it. Not often, but inevitably. Now here's the micro versus macro divide. At the microscopic level, there is no concept of explosion or destruction. There are only interactions, forces, probabilities, particles rearranging into more stable configurations. But at the macroscopic level, our world, that rearrangement becomes heat, shock waves, light. The laws at the bottom are calm and indifferent. The outcomes at the top are dramatic And this is the disturbing part Feynman hinted at. Nature is not violent. Nature is consistent. When you split an atom, the universe is not angry. It is simply obeying its own accounting system. Energy must be conserved. Forces must balance. Entropy must increase. Entropy. Let's talk about that. Analogy number 3, ice melting. Put an ice cube on a table. It melts. Talk about that. Why, Jet? That because there are far more ways for water molecules to be disordered liquid than ordered solid. The universe prefers disorder, not because it wants to, but because disorder is statistically overwhelming. Now apply that idea to nuclear reactions. Heavy elements like uranium are, in a sense, low entropy arrangements of matter. They were forged in the violent cores of supernovae, stars exploding under gravity. They are rare, complex configurations when they split into smaller nuclei. Those fragments are statistically more stable, more probable. Entropy increases, energy spreads out, heat dissipates. From the perspective of thermodynamics, nuclear fission is simply matter relaxing into a more probable state. The bomb is not a violation of nature. It is nature taking the fastest route toward equilibrium. But let me push this further. You might think, fine, that explains bombs. But what about nuclear power plants? What about controlled fission? Good question. Good question. A nuclear reactor is not defying entropy, it is guiding it. We insert control rods to absorb neutrons. We slow down the chain reaction. We let the energy leak out gradually instead of explosively. But the direction is the same. Energy flows from concentrated to dispersed, order to disorder. Always, the laws of physics say no to perpetual stability. Everything complex is temporary. And here's where it gets uncomfortable. You are also a temporary arrangement of energy. Your body is made of atoms forged in stars, carbon, oxygen, iron, assembled into something improbably ordered. You are low entropy. You are tension held together by forces and information. And just like uranium, that arrangement will not last forever. Now before you panic, this is not nihilism. This is physics. Let me ask you something. Why doesn't your body fall apart right now? Because you're not a closed system. You eat. You breathe. You exchange energy with the environment. You fight entropy every second. Life is not defying the second law of thermodynamics. It is riding it. You increase the entropy of the universe faster than you increase your own. That's the deal. You burn fuel. You radiate heat. You export disorder to stay ordered. Just like a nuclear reactor exports heat, biology is physics in slow motion. There is no magical life force. There is chemistry and energy flow. But here's the philosophical pivot. The same laws that allow atoms to split are the laws that allow stars to shine. The sun works through nuclear fusion. The opposite of fission, small nuclei combine into larger ones. And again, a tiny bit of mass becomes energy. That energy travels 150 million kilometers, warms your skin, powers photosynthesis, builds forests, builds you. The disturbing power of splitting the atom is the same power that made you hot. Existence possible. We didn't invent nuclear energy. We discovered a rule that has been shaping the cosmos for 13.8 billion years. The universe has been running on nuclear reactions since the first stars ignited. When we split an atom, we are not playing God. We are touching the engine room of reality, and the engine doesn't care who touches it. That's what unsettles us. We expect moral feedback from nature. We expect a warning label written into the atoms. But physics is silent. The strong force binds. Electromagnetism repels. Entropy increases. Always, no exceptions, you might ask. Could we just choose not to use this knowledge? That's a human question. Knowledge itself is neutral. Once you understand the forces inside the nucleus, the implications follow. The laws of physics say, if you arrange matter this way, this will happen. Not maybe. There is something brutally honest about that, and something beautiful, because it means the universe is understandable. Feynman once said the pleasure of finding things out is one of the greatest joys. When we split the atom, we weren't breaking nature. We were understanding it deeply enough to predict its behavior. The disturbing part is not the atom. It's us. We are creatures evolved to survive on a savanna. And now we hold equations that describe the heart of stars. We have hands shaped by evolution and knowledge shaped by mathematics. That gap is enormous. But here's the realization I want you to sit with. The energy in the nucleus was always there. The laws governing it were always there. The stars have been splitting and fusing atoms long before Earth existed. What changed is that a small temporary arrangement of carbon, You learned how to ask why. Why does the nucleus stay together? Why does it split? Why does mass become energy? And that is astonishing. Yes, splitting an atom can level cities. But it can also power hospitals. It can light homes without carbon emissions. It can propel spacecraft. The same equation. Different intentions. The laws don't choose, we do. And maybe that's the most unsettling truth of all. The universe gives us power, but not instructions. So let me end with this. When you look at your hand, you're looking at atoms held together by electromagnetic forces. Deep inside them are nuclei held together by the strong force. Inside those nuclei is mass that could become energy. But most of the time, it doesn't, because the universe balances on probabilities. On stability, because the universe balances on probabilities. On stability, on statistics. The world doesn't explode because most configurations are stable enough. Long enough for planets to form, long enough for life to emerge. Long enough for you to sit here watching this thinking about splitting an atom. That's the miracle, not the explosion. Not the explosion, the narrow window where order persists against overwhelming odds. The disturbing truth is that matter contains unimaginable energy. The comforting truth is that the laws governing it are precise, predictable, and universal. We live in a universe where tiny differences in mass can light the sky, where entropy pulls everything toward disorder, and where, for a brief moment, complex structures like you arise to understand it. So here's my question for you. Knowing that the power of stars sits quietly inside every atom around you, does that make the universe feel more terrifying? Or more beautiful? Let me know what you think, because the fact that we can even ask that question might be the most extraordinary thing of all.